Welcome back to our channel, where we dive deep into the mysteries of the universe with the help of renowned physicist Brian Cox. Today, we're exploring a mind-bending concept: something massive existed before the beginning of time. Strap in as we break down this complex idea into 5 engaging segments. Don't forget to like, subscribe, and hit the bell icon to stay updated with our cosmic journeys. Let's delve into the mysteries preceding the Big Bang. It's crucial to define our terms precisely. When we speak of the Big Bang, we're referring to that pivotal epoch when the universe was extremely hot and incredibly dense. This isn't up for debate, it's a visible truth when we gaze into the cosmos. The leading theory, and one that Brian Cox has recently explored in depth, suggests there was an era prior to this known as inflation. This is a significant breakthrough in understanding the origins of the universe, addressing age-old questions about the universe's very existence. Observing the stars, planets, and galaxies, we inevitably stumble upon a profound enigma: why does anything exist at all? This question becomes even more intriguing considering the laws of physics which, intriguingly, treat matter and antimatter symmetrically. Yet, our universe is predominantly matter, with scant antimatter. This fundamental asymmetry has shaped our world and remains one of the most challenging puzzles. So, what preceded the universe and time itself? Brian Cox has ventured into these depths to offer new insights. While the classical view supported by Einstein's theories and standard cosmology presents the Big Bang as the universe's beginning, it's now clear there was a significant phase before that, setting the stage for everything we observe today. Imagine defining the Big Bang as a moment when the universe, from a state unimaginably hot and dense, suddenly burst forth about 13.8 billion years ago. This intense phase is known as inflation. What we believe occurred is a period of rapid, almost unfathomable growth where the universe expanded exponentially, doubling in size again and again. Consider this: the universe started smaller than a single atom and, in a flash, expanded to exceed the size of our observable universe with its 350 billion galaxies, all in less than a blink of an eye, a tiny fraction of a second. When this explosive expansion finally halted, all the energy that fueled it transformed. It heated the cosmos, creating the particles of matter that constitute everything we are and everything we observe in the night sky. This phenomenal event is what we recognize as the Big Bang. It might sound like a flight of fancy, but this is the essence of current standard cosmology. The real puzzles remain: what initiated the inflation? What caused it to stop? How long did this inflationary period last? As of now, the answers remain elusive. For centuries, scientists have grappled with these questions. For centuries, the prevailing belief was that the universe had always existed, a vast clockwork of stars and galaxies ticking eternally according to the laws of physics. But in 1927, a paradigm shift was sparked by a Belgian priest and physicist named Georges Lemaitre. He proposed a radical idea: the universe had started as a gigantic, primeval atom, which had exploded, scattering the smaller atoms that formed the cosmos as we know it. Initially, Lemaitre's theory didn't catch much attention. But everything changed in 1929 when astronomer Edwin Hubble made a groundbreaking discovery: the universe was expanding. This suggested that if we could rewind the cosmic tape, everything would converge back to a singular, infinitely dense point. This idea, mockingly dubbed the Big Bang Theory by astronomer Fred Hoyle, would soon become a cornerstone of modern cosmology. Despite skepticism, the idea gained traction. Scientists Ralph Alpher, George Gamow, and Robert Herman predicted a residual afterglow from the Big Bang should still be lingering in the cosmos, a faint echo of the universe's explosive dawn. Finding it, however, would require an incredible stroke of luck. That luck arrived in the mid-1960s when astronomers Arno Penzias and Robert Wilson were plagued by a persistent, inexplicable hiss in their radio antenna, a noise no repairs could fix. Unbeknownst to them, this noise was about to turn into one of the most significant discoveries in astrophysics. The faint echo of the Big Bang, known as the cosmic microwave background (CMB) radiation, holds the key to understanding how our universe came to be. But how did that initial explosion lead to the formation of the planets, stars, and galaxies we see today? Through meticulous calculations and observations from both Earth-based telescopes and space probes, scientists have pieced together an incredible story. Approximately 13.8 billion years ago, all the matter in the universe emerged from an unimaginably small point, or singularity, in a violent burst of energy. This initial explosion caused the universe to expand at a mind-boggling rate, doubling in size every tiny fraction of a second, specifically, every 10 to the power of -34 seconds, creating the very fabric of space as it expanded. Within the blink of an eye, gravity and other fundamental forces began to take shape. Energy converted into particles of matter and antimatter, which mostly annihilated each other. However, a small excess of matter survived. Protons and neutrons began to form within the first second, and within minutes, these particles fused to create the nuclei of hydrogen and helium. About 300,000 years later, these nuclei captured electrons, forming the first atoms and creating vast clouds of hydrogen and helium gas throughout the universe. Around 380,000 years after the Big Bang, the universe had cooled enough to allow photons to travel freely, leaving behind a bath of radiation known as the cosmic microwave background. This radiation, which Arno Penzias and Robert Wilson accidentally discovered, carries within it the faint ripples that would eventually grow into the stars, galaxies, and planets we see today. During the period of inflation, tiny fluctuations in matter rapidly expanded, eventually becoming the seeds from which galaxies and galactic clusters would form. Observations of the universe, despite some uncertainties, consistently reveal a cosmos dominated by matter that adheres to the same physical laws everywhere, at all times. Governed by general relativity, the universe continues to expand and cool, influenced by the mysterious forces of dark matter and dark energy, with normal matter, neutrinos, and radiation making up the rest. Today, the universe is a vast and intricate tapestry filled with galaxies, stars, planets, heavy elements, and, in at least one known place, intelligent life. These structures didn't appear overnight, they emerged through a complex process of cosmic evolution. In the 20th century, scientists made a groundbreaking achievement by reconstructing the timeline of the universe's evolution, tracing it from a mostly uniform mix of hydrogen and helium to the rich, diverse structures we see today. By looking back through time, we can investigate the origins of every cosmic structure and component. For each discovery, we ask, where did it come from, and how did it arise? This relentless pursuit of knowledge takes us to the very edge of our understanding, leading us to ponder how everything in existence emerged, and whether it could have all come from something beyond our current grasp. The life we know today traces its origins back to tiny particles that make up everything around us. These particles act as the fundamental building blocks, combining to form complex molecules essential for life. At the heart of these building blocks are atoms, the basic units that compose everything in the universe. The formation of atoms was a lengthy and intricate process. Stars had to be born, live out their fiery lives, and eventually die in spectacular explosions, creating new elements through powerful reactions. These elements then seeded the formation of new stars, continuing the cosmic cycle that is essential for the existence of planets and the complex chemistry needed for life. For stars and galaxies to exist, several crucial events had to unfold. Gravity played a key role, pulling smaller groups of stars and galaxies together to form larger structures. This process required an initial mass, which grew by attracting more matter through gravity's pull. Dark matter, an invisible but vital component, was also essential in the early stages, preventing matter from dispersing into space during star formation. The creation of the universe itself depended on a precise balance of matter and radiation. This delicate mix produced phenomena like the afterglow of the Big Bang and the fundamental elements necessary for galaxies to form. Without these key events, the universe as we know it, and everything within it, would not exist. Slight variations in the density of matter were essential for the formation of the universe as we know it. These tiny imbalances grew over time, driven by the force of gravity, and played a crucial role in shaping everything from galaxies to stars. The interplay between dark matter and ordinary matter, along with these initial density fluctuations, laid the foundation for the development of the complex structures we see today. When we ponder whether the universe could have originated from nothing, these unresolved factors become particularly significant. In physics, matter and antimatter are typically treated as equals, meaning they should be created and destroyed in equal amounts during reactions. However, at the universe's inception, extreme heat and density could have produced large quantities of both. Despite this, the universe ended up with more matter than antimatter, defying the expectation of balance. Several theories attempt to explain this mysterious imbalance, but the exact mechanism remains elusive. These processes involve three key elements: special conditions where imbalances arise, which occur as the universe expands and cools, and processes that disrupt the normal rules to produce more matter than antimatter. The standard model of physics tries to account for this through specific interactions known as Sphaleron interactions, which generate a particular type of asymmetry. The standard model of physics suggests a subtle violation that favors the production of matter over antimatter. However, while these ideas are part of the standard model, they don't fully explain the mystery. If we imagine a universe with equal amounts of matter and antimatter as essentially a universe with nothing, then it seems our universe somehow created something from nothing. Yet, the exact mechanism behind this remains unknown. Similarly, when it comes to dark matter, extensive research has shown that it doesn't consist of particles found in the standard model. Dark matter, which makes up a significant portion of the universe, requires a new understanding, new physics beyond what we currently know. There are several theories about how dark matter might have formed. It could have been created during the universe's early, hot phase and remained stable ever since. Alternatively, it might have emerged during a phase change as the universe expanded and cooled, existed as a different type of neutrino, or perhaps resulted from gravity creating an extremely heavy particle. But this raises an intriguing question: why do we have dark matter today when the early universe seemed to function without it? There must have been a process that brought dark matter into existence when it wasn't there before. Understanding this process is crucial to unraveling the full story of our universe's formation. All these mysteries remind us that while we've made incredible strides in understanding the universe, there's still so much more to discover. One of the big questions in cosmology is where the energy that powers the universe came from. According to our leading theory, cosmic inflation, this energy might have come from nothing. When we think about the beginning of the Big Bang, we often picture a superhot, densely packed, and energetic state. But how did this come to be? There are two ways to approach this question. One way is to simply accept that the universe was born this way, without further explanation, a view that, in theoretical physics, can feel like giving up. The other way is to develop a theory that explains these initial conditions, offering new predictions that we can test. This is where cosmic inflation comes into play. Instead of imagining the universe starting as an infinitely tiny, infinitely hot point, inflation suggests a different scenario. Before the Big Bang, space was filled with an incredibly high energy density. This energy caused the universe to expand at an astonishingly rapid pace during inflation. When inflation ended, this energy transformed into matter, antimatter, and radiation, setting the stage for the hot Big Bang that followed. Cosmic inflation not only explains how the universe ended up with a uniform temperature and a flat appearance, but it also predicts specific density variations that we observe today. These predictions make inflation a powerful theory that continues to shape our understanding of the universe's origins. Observations of the universe confirm the variations predicted by cosmic inflation, showing how the entire observable universe, with all its complex structures, could have emerged from what seemed like almost empty space filled with energy. This idea provides a fascinating explanation for how the universe could have arisen from seemingly nothing. However, for many, this concept is still difficult to grasp. Imagining a universe without space, time, or physical laws challenges our understanding. Yet, to truly consider the origins of everything, we might need to envision states beyond space, moments beyond time, or conditions that are not bound by physical reality. These ideas may serve as steps toward understanding a true state of nothingness. But it's important to note that philosophical nothingness differs from the scientific view of nothingness. Scientifically, there are 4 ways to define nothing, each with its own context: a time when something didn't exist, an empty space, space-time in its most minimal state with the lowest possible energy, and what remains when you strip away the entire universe and its laws. Using the first 2 definitions, we could argue that the universe indeed started from nothing. But the third definition, space-time at its emptiest, adds complexity to this view. Our current knowledge isn't enough to fully explore the concept of nothingness, especially without a scientific theory that describes what lies beyond the universe and its laws. In physics, true nothingness lacks a clear definition. It's challenging to comprehend how space and time could emerge from a state of non-existence. How can spacetime come into being at a specific location or moment when those very concepts don't exist? And without spacetime, where do the rules governing quantum fields and particles originate? This perspective suggests that spacetime and the laws of physics might not be eternal, though proving or disproving this idea depends on assumptions that aren't well established, particularly for the extreme conditions we would need to apply them to. If we defined nothing in a physical sense, it might appear that the universe emerged from nothing. But when we step outside the constraints of physical laws, our certainty about the origins of the cosmos fades. Many scientists propose that the universe could have sprung from nothing, an idea grounded in quantum theory. This theory suggests that quantum fluctuations might have triggered the spontaneous creation of a universe from nothingness. However, this idea lacks strong evidence, and the mystery of our cosmic origins remains unsolved. What do we mean when we say, the beginning of time? Time, as we understand it, is a measure of change within the universe. But according to Brian Cox, to comprehend what existed before time, we must first redefine our perception of time itself. Let's unpack how scientists view time in relation to the universe and why this question challenges the very foundation of modern physics. Cox suggests that something massive might have existed before our universe began with the Big Bang. Here, we delve into theories like the multiverse, where an infinite number of universes could coexist, each with its own beginning and end. This segment explores whether our universe is just one of many bubbles in a cosmic foam. Quantum mechanics might hold the key to understanding pre-time phenomena. At the quantum level, particles pop into and out of existence. Could the universe itself behave similarly on a cosmic scale? We explore how quantum theories could explain the origins of the universe and what might have existed before it. Brian Cox isn't just a physicist, he's a pioneer in making complex scientific concepts accessible. In this segment, we examine his contributions to our understanding of cosmology and how his ideas inspire us to look beyond conventional scientific boundaries to answer the question of what existed before the Big Bang. What does this mean for future scientific research? Understanding what existed before time could not only redefine our knowledge of the universe but also pave the way for technological advancements in physics. We discuss the potential impact of these theories on future explorations and how they might one day answer the ultimate question of our cosmic origins. Eternal inflation is a theory suggesting that inflation never stops entirely, it only ceases locally, which gives birth to individual universes. This segment will explore how the concept of eternal inflation fits into the idea that something massive may have set the stage for the Big Bang and subsequent universe creation. String theory provides a framework for considering pre-Big Bang scenarios. This segment dives into how string theory suggests the universe could be one of many brains, floating through a higher dimensional space, possibly interacting with others to create Big Bang-like conditions repeatedly over time. Energy. What role do dark matter and dark energy play in the cosmos, especially before the Big Bang? This segment examines theories suggesting that these mysterious components could have dominated the pre-universe phase, influencing its structure and evolution. The question of what existed before time invites not only scientific inquiry but philosophical speculation. We'll discuss how different philosophies approach the concept of before time and the existence of the universe. What technologies are scientists developing to study such profound cosmic questions? This segment highlights the cutting-edge tools and experiments, like the Large Hadron Collider and space telescopes, that may provide insights into the state of the universe before the Big Bang. Gravitational waves have opened a new window into observing cosmic events. We will explore how these waves might help us detect signals from before the Big Bang, offering clues about the universe's earliest moments.
Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.